Hey, everybody. So we're going to take a look at a hydraulic jack. Now here I've got a jack that picks up 2 tons. Now remember that a ton is 2,000 pounds. So this little jack can pick up 4,000 pounds because it can pick up 2 tons. So that's pretty cool. So how does this work? Well, there's some information that we need to know. First, we need to know the size of our output cylinder. That's really important. Every time I pump this, notice that goes up. So that's how we raise things. If I flip this over, we're also going to need to know the diameter of that cylinder. So there's a combination of really cool math that happens between this and this to make this raise up. One of these days, I may take this apart and see if this is bigger inside here than it's shown here, because I think that would change some things a lot as well. There's another thing we're going to have to remember is that when I jack this up, when I take my jack and see I've got a little pump thing and this makes it go up, right? So it's going to make it jack up. If I take this handle right here and I put it in this jack, it gives me a whole bunch of mechanical advantage. And we're going to take a look at the math behind all of this in this presentation. We're going to see how this little tiny cylinder makes a huge difference in this great big cylinder and how these two things interact. So stay with this, stick with me. It's going to be pretty simple, but it's a complex task at the same time. So please seek me out if you have questions. So let's get started behind the theory. Hey, so now that we've taken a look at a hydraulic jack and what it looks like, let's see how it works. So our jack, we already know can pick up 4,000 pounds. And there's two things that we're going to need to know about that jack. So we're going to kind of take a look at these and move through quickly. But our input cylinder is 3/8 of an inch in diameter, and our output cylinder is 7/8 in diameter. Now, those are important because there's a relationship, there, a ratio that happens that the smaller the cylinder, the less force it will put out. So we'll kind of explain that here in a second. So we need to do a couple things. Because of our situation, and we see down here, I'm going to kind of circle this so you can see what I'm talking about. This is the picture of our jack. We have an output cylinder here that's 7/8. We have an input cylinder here, which is 3/8. So there's our 3/8 and there's our 7/8. And I've already converted those to decimals because it makes it a little easier for us to deal with. So how do we calculate input force? We're going to deal strictly with this cylinder first because that's what we're looking for. But we're going to find that we cannot do that yet. So how do we do this? Well, we need to know the formula for pressure. And the formula is force per area. And that we've been using for quite some time. And the very first thing we need to do is figure out what the output pressure is, because if we need to know force and area, we know the force here, and we need to calculate the area of this. So to do that, pressure is force per area. Our pressure is 4,000 pounds divided by pi r squared. And we know that from previous lessons that pi r squared is the area of a circle. So knowing that, we're going to take 3.14 times 0.4375. And you're going to say, whoa, wait a minute. Why are we using 0.4375? We're using 0.4375 because this symbol, remember, right here from previous lessons, we know that's a diameter symbol. And if that's a diameter symbol, you need to divide that by 2 to find its radius. That's where 0.4375 came in. So we do the math on that. We take 0.4375 times 0.4375 because remember, this radius right here has to be squared. Being that it has to be squared, it's multiplied by itself. That means you take 0.4375 times 0.4375. And that ends up being 0.19. Now all we have to do is take 3.14 times 0.19, and we're going to end up with 0.6. And you can do the math on your calculator if you want to. So now it's a matter of taking 4,000 pounds divided by 0.6, and that's going to give us our output pressure, or the pressure on this cylinder. And what's unique about hydraulic jacks is that the pressure here matches the pressure here. It still isn't clear on how this is going to work, but we're going to keep going. So the next thing we need to do is take a look at our input cylinder. And remember, our input cylinder is this cylinder here. And we know that we have a pressure now for that cylinder because the pressure inside the system is the same because it's a sealed system. So how much force will I put in? Well, remember, we have to rearrange this formula. And you can use number substitution, or you can use the thumb chart, whichever you like the best. So when we rearrange that, we end up with force equals pressure times area. And remember, area is pi r squared. So we're going to have to go through that r squared thing again for 0.4375. So what I did is, remember, this symbol right here is a diameter symbol, which means we have to take this number and divide by 2, which ends up being 0.1875. That's where we got that number. And remember, to square something, we take and multiply by itself. When we do that, we end up with 0.4 square inches. So we're going to take 3.14 times 0.4, and that's going to give us a number of 0.13. I know this is a lot of numbers. I'm just kind of whittling away over here, whittling away at this stuff over here. So now I've got 6,667.67 pounds divided by 0.13. It's going to be a huge number, 866 pounds. That means I have to push down on this cylinder with 866 pounds. It can't be done. I cannot do that physically. We know my hydraulic jack will pick up 4,000 pounds, but I need to input that much force. That's ridiculous. Can't do it. So how the heck does this work? I want you to think back. I showed you a lever. Remember that? I showed you a lever, which means that we have a central point here that we're going to pivot around, and this is going to be pushed downward. You're starting to get a hint here? How is this going to work? How are we going to do that? Come on, think about this. Think about it. We have a handle. Could be called a lever. I got a force here. I got a length of a lever arm here. You're right. We're going to use torque. So torque, remember, is force times length. And how do we do this? Well, we do this by doing a little bit of math here. And what's going to be interesting is we're going to see how this works. So we're going to take a look at torque. I'm going to write this out here, equals force times length. And when we do that, we know we have an 866 pounds. I know this is ugly writing. I apologize for that. Times the length. Remember, the length is 12, but this is in inches. So that means our length has to be in feet, which is 1 foot. We do a calculation there. And that's going to equal torque. Wait a minute. That didn't work either. We're still putting in 866 pounds of force on this arm to make this jack move. It doesn't work. Oh boy. Let's take a look at this further detail. So we're going to take a look at the formula for torque times length, and we're going to solve for the torque on the arm, which we just did. But here's the kicker. I've thrown in this other number here. Technically, when we look at our jack, we have a pivot point that the jack's pivoting on here, and we have where the force gets input here. So technically, the length of our lever arm is only this, which is 1 inch, and 1 inch is 0.08 feet. Ooh, this looks like a more doable number. We're only going to need to input 69.3 pounds. I know this is a very confusing concept to look at so quickly. Please watch this again. There's a tremendous number of numbers here. Look for another video of how to solve these problems, because there's a really cool method that we can use. This is the long way. Please look this over, commit this to memory, and we're going to take a look and see if we can boil this down to some simple steps that we can use later. As always, contact me with questions. I look forward to helping you.